Hello and welcome to this Bio43 pre-lab video. Today we're going to start with an overview of statistical tests. This will of course tie into our learning objectives about using statistics to analyze and effectively communicate experimental results. Let's imagine a generic experiment. We have two treatments, A and B, and we want to know if the difference in treatment affected the dependent variable. So we make our measurements and see if the values for treatment A are different from those for treatment B, which they are. But obviously they are. As we discussed last week, unavoidable sources of random error will always cause measurements to be different. If we took 10 measurements from treatment A, and then 10 more measurements from treatment A, they would be different. So when we see the data from treatment A and treatment B, we have to ask, are the differences due to the change in the independent variable, or just the inherent randomness of the system? Let me show you 4 different data sets. In a moment, I want you to pause the video and do 2 things. First, I want you to order these data sets from the one where you think the independent variable is most likely to have caused the difference to the one where it was least likely to have caused the difference. Most people do this intuitively, so the second thing I want you to do is take a moment and think about what criteria you use to make your list. Think about that now. When given the task of ordering these datasets, nearly everyone agrees that graph 1 is a scenario where the independent variable most likely had an effect, and graph 4 is the one where it was least likely. There tends to be disagreement about how graphs 2 and 3 should be ordered. So let's talk about why that is. The criteria that students use to order these graphs typically come down to 2 things: variation between the datasets and variation within the datasets. Variation between sets is commonly referred to as signal. How different are the centers of the datasets? We previously established that the mean is the parameter we use for determining the center of data. So signal can be expressed as the difference between the means. The larger the difference, the stronger the signal. This should make sense. If the independent variable has an effect, the mean should change. The second criterion was variation within the set. Essentially, how spread out are the data points within each treatment? This is commonly called noise, and is measured by the variance, or the standard deviation, which we mentioned back in the AIR video. The 95% confidence interval can also be thought of as a measure of noise. The larger the 95% confidence interval, the wider the range in which the true population mean could lie. So even when we see a difference between the sample means, the higher the noise is, the less confident we are that the population means actually differ. This explains the ranking of these graphs we did. We ranked graph 1 highest because it has high signal and low noise, while we ranked graph 4 at the bottom due to the low signal and high noise. 2 and 3 were harder to classify since the former had low signal and low noise, while the latter had high signal but also high noise. We can't always intuitively process signal and noise, so we need statistics. The statistical tests we use are signal-to-noise ratios. For example, this is a formula used for a t-test, a test we'll learn more about in the next video. You won't have to use this equation yourself. I'm just showing it to you to illustrate a point. The numerator for the equation is the difference in means, our definition of signal. Standard deviation, a measure of noise, is part of the denominator. So this equation is literally a ratio of signal to noise. The higher the value of the t-statistic, the more likely the difference in data is due to the independent variable and not random fluctuations. Let me briefly mention sample size again here. We previously discussed how larger sample sizes lower the 95% confidence intervals. Now we see it in this equation, and the larger the n values, the larger the t-statistic will be. This is another reason why it's better to have large sample sizes. Different tests will give us different test statistics, which are all hard to interpret by themselves. But we use these test statistics to get p-values. I mentioned these back in a video from week 1, but to reiterate, the p-value is a probability of getting data as or more extreme than these results if the null hypothesis is true. So if the null hypothesis is true, if the independent variable had no effect, and the difference between the datasets is entirely due to the inherent randomness of the system, these are the odds of getting data like what you collected. So the lower the p-value, the more likely we are to reject the null hypothesis. If we have a p-value of 0.02, there's only a 2% chance of collecting data like this if the null hypothesis is true. Previously, we talked about using an alpha of 0.05. We are willing to wrongly support the alternative hypothesis 5% of the time. So if the p-value is less than 0.05, we reject the null hypothesis and support the alternative hypothesis. If the p-value is greater than that, we fail to reject the null hypothesis and say the alternative hypothesis is not supported. Future videos will walk you through the specifics of various statistical tests, but it will always boil down to finding and interpreting a p-value in this way. The next 2 videos will deal with t-tests and ANOVA, and future units will deal with other forms of analysis. See you next time!